Imagine a bowling ball on a trampoline. It doesn't pull a nearby marble towards it with some invisible rope. Instead, the heavy ball warps the fabric of the trampoline, creating a dip. The marble, trying to roll in a straight line, finds its path curved by that dip and spirals inward. This is the heart of Albert Einstein's revolutionary idea, general relativity. He told us that gravity isn't a force reaching across space, it's the shape of space itself, or more accurately, space-time. Massive objects don't pull on other objects, they tell space-time how to curve, and space-time in turn tells other objects how to move. It's an elegant cosmic dance choreographed by mass and energy. This simple yet profound concept explains so much about our universe. Think about our own solar system. Earth isn't being tethered to the sun by a gravitational string. We are simply following the straightest possible path through the curved space-time created by the sun's immense mass. We are, in a sense, free-falling through a valley in the cosmos. This curvature of space-time is what we experience as gravity. During a solar eclipse in 1919, astronomers saw starlight from behind the sun bend just as Einstein predicted. One of the most stunning predictions Einstein made was that even light, which has no mass, should have its path bent by gravity. And this isn't just some abstract astronomical phenomenon. General relativity affects you every single day. The Global Positioning System, or GPS, in your phone relies on a network of satellites. Their clocks tick just a tiny bit faster than ours down here. Now let's explore a different, more speculative idea. What if the universe isn't just a fabric, but a giant musical instrument? Imagine everything that exists is a vibration, a note in a grand cosmic symphony. This is the core of the resonance ladder concept. In this view, the entire universe is a four-dimensional resonator, a structure where frequencies can exist and stack, from the very slow to the incredibly fast. Each level of this ladder, each rung, represents a fundamental frequency, where particular phenomena can manifest. It's a radically different way of thinking about the cosmos. Think about the scales of vibration we already know. The incredibly high-frequency oscillation of the Higgs field, giving particles their mass. The much slower, familiar rhythm of your own breath, a biological oscillation that sustains life. And spanning the entire cosmos, the faint cold hum of the cosmic microwave background radiation. The resonance ladder idea proposes these aren't separate phenomena. They're harmonics of a single underlying structure. In this model, gravity takes on a whole new identity. It's not a particle like a hypothetical graviton. It's not the bending of a physical sheet of space-time. Instead, gravity is what happens when the universe's frequency structure gets distorted. Place a massive object, like a star, into it. It alters the spacing between the rungs. One of the biggest challenges in modern physics is a profound disagreement between our two best theories of the universe. General relativity, our theory of the very big, describes gravity and the cosmos with stunning accuracy. Quantum mechanics, our theory of the very small, describes the bizarre world of particles and forces with equal precision. But they don't play well together. When you try to use them in the same place, inside a black hole or at the moment of the Big Bang, the math breaks down into nonsense. This is the great puzzle: how to unite gravity with the quantum world. The resonance ladder idea offers a potential, though unproven, path forward. By describing gravity as a feature of a universal frequency structure, it sidesteps one of the main stumbling blocks. Standard quantum theory suggests that forces should be carried by particles. For gravity, this would be the graviton, a particle that has never been detected. The latter model says you don't need a graviton. Gravity isn't a particle-based force, it's a distortion in the underlying vibrational background of the cosmos. This could potentially resolve the conflict by reframing gravity in a language of frequencies that might be more compatible with the quantum world. This new perspective doesn't just try to solve old problems, it makes new, testable predictions. If gravity is truly a distortion of a frequency ladder, then we might see subtle extra effects that general relativity doesn't account for. For instance, we could look for tiny, unexpected distortions in the spectra of distant stars or galaxies. The spacing between spectral lines might be slightly different than we expect. We use those lines to identify elements across the cosmos. These deviations would be a signature of the ladder's rungs being squeezed or stretched by gravity, distinct from the predictions of pure space-time curvature. Furthermore, this model offers a tantalizing alternative to another cosmic mystery: dark energy. In the latter model, the cosmic expansion could be explained by the fundamental ratio, alpha, changing over cosmic time. Now we have to be honest. It's one thing to have a beautiful idea, it's another for that idea to accurately describe reality. The resonance ladder hypothesis faces some enormous challenges. Probably the biggest one is the monumental success of general relativity. For over a century, Einstein's theory has been tested again and again, and it has passed every single test with flying colors. Precise orbits of planets, ripples of gravitational waves from merging black holes. Any new theory hoping to replace it has an incredibly high bar to clear. The latter idea, at least in its current form, is not yet a complete theory. It doesn't yet match all the observational results that general relativity explains so perfectly. A key part of the model is the ratio alpha. It's said to change with matter density. But right now this value is essentially fitted to make the model work, rather than being derived from first principles. A theory is stronger when components are predicted, not just adjusted to fit data. A graph with overfitting example, data being forced to match curve. The nature of alpha remains one of the biggest unanswered questions, making the model more sketch than finished portrait. Furthermore, some specific predictions of the latter model, subtle spectral distortions, different line spacings, haven't been observed yet. They could be too small for our current instruments to detect, but a theory lives and dies by its testable predictions. Until these unique effects are found, the resonance ladder remains fascinating but speculative. The absence of evidence is not evidence of absence, but we must remain skeptical and demand rigorous proof before rewriting physics textbooks. So where does this leave us? We have two very different pictures of gravity. On one hand, we have Einstein's masterpiece, general relativity, which tells us that the universe is a dynamic stage of spacetime. Massive objects bend this stage, and the curvature they create guides the motion of everything else. It's a theory of geometry, tested and confirmed, that describes the cosmic dance of planets, stars, galaxies. The redshift we see from distant galaxies is the stretching of the spacetime fabric as the universe expands. It is the reigning, undisputed champion. On the other hand, we have a bold challenger, a universe as a four-dimensional resonance ladder. Reality is fundamentally vibrational. Gravity isn't the bending of space, but the bending of the universe's frequency structure. Matter, energy, distort the spacing of the resonant rungs, and this distortion is what we experience as gravity. It's a theory of harmony and dissonance. Both models agree on redshift. One calls it the stretching of spacetime, the other calls it a change in fundamental resonant frequencies. They describe the same effect in different languages. Why bother with a strange new idea when general relativity works so well? Because that's how science advances. We push at the edges of knowledge, we ask, what if? And we propose alternatives. Even if an idea is wrong, testing it yields discoveries and deeper understanding. The resonance ladder forces new thinking and predicts subtle effects we can design experiments to find. The search itself is valuable. Observation and evidence will decide. The universe is the final arbiter. Does the cosmos behave like a bending fabric of spacetime or a vibrating ladder of frequencies? GR says spacetime bends. The resonance ladder says the universal frequency scale bends. It predicts tiny fingerprints in starlight. Our quest is to build instruments sensitive enough to look for them. Whether we find them or not, the journey to understand gravity is one of the grandest adventures in science.